This is the lecture for lesson 28. The first part of this section, we are going to talk about how we can relate logarithms and exponents, and we're going to convert between the two. So logarithms and exponentials are opposites, just like addition and subtraction are opposites of each other, and multiplication and division, and squares and square roots. So what we have is, if we know we have a base to an exponent equals some answer, we can use logs to say that the log base b of a is equal to the exponent. So if the log base b of a positive number a we have this following, we need to remember that a has to be greater than or 0, the base has to be greater than 0, and the base cannot equal 1. Then we can translate it into exponential form here. So the way that I try to remember this is log of b. So b stands for base to the exponent equals the answer. So BAE, log BAE, and then we can transform it into exponential form. So log of 5 of 25 is 2. So what that means, 5 is the base, that 25 is the answer, and 2 is the exponent, log of BAE, log of bay. So we can rewrite that as 5 squared equals 25. The base to the exponent equals the answer. So log of 64 equals 3. The way I rewrite that, so BAE is the base, 4 to the exponent 3 equals the answer 64. And the last one, log base 9 of x equals 7. So base, answer, exponent, 9 to the 7th equals x. So what we can do is we can use these logs and these moving around back to exponential form to be able to solve for a missing variable. So without doing any calculations, let's decide if this is correct. So we know the log base 5, so there's the base, 125 is the answer, and then y is the exponent. So let's flip it around. The base is 5, the exponent is y equals the answer, 125. Yes, this was done correctly. Now we're going to have them in exponential form and be asked to write them back in log form. So we're going to, again, have base to the exponent equals the answer, and we're going to now go this way to log base b of the answer equals the exponent. So the base is 5, the exponent is -3, the answer is 125. So log base 5 of 1 over 125 equals the exponent -3. In b, the base is 15, the exponent is 2, and the answer is x. So log the base of 15 of the answer x equals the exponent 2. And the last one, the base is 11, the exponent is y, the answer is 300. So log base 11 of 300 equals y. The next thing we're going to do is actually evaluate some logs using that exponent property, giving us positive and negative answers, and then talk about what are the common logs and natural logs. The first one they want us to evaluate is log base 6 of square root 6. So what I'm going to do is I'm going to set that equal to x. Log base 6 of square root 6, I'm going to set equal to x because my goal is to find the answer here. Well, we know according to the logs, this is the base, answer, exponent. So I'm going to translate this into the exponent form. So base 6 to the exponent x equals the answer square root 6. Now, we've worked with solving some exponentials before. So what I'm going to do is I'm going to rewrite these. So some things we need to remember. A square root is a power of 1/2. So I can rewrite the square root of 6 as 6 to the 1/2 power. When my bases are the same, we then set the exponents equal. So the answer to this one is 1/2. So this original problem is saying 6 to what power gives me square root 6? Well, 6 to the 1/2 power gives you square root 6. Okay, looking at B, log base 8 of 2 is going to give me what? So this one is saying 8 to what power gives me 2? So let's rewrite that as 8 to what power gives me 2? Well, right now these bases are not the same, but I know that 8 is 2 to the 3rd power. So I'm going to make that 2 to the 3rd power to the x equals 2. Which means that's 2 to the 3x equals 2. And now my bases are the same, so all I need to do is work with their exponents. There's an invisible 1 exponent here, so 3x equals 1. If I solve for x, x is going to equal 1/3. So we can have fractions, or we can have round numbers. Next one's a little faster to figure out. This one's saying 7 to what power gives me 49? And that one you guys should know is 2. 7 squared is 49. So there's your first set. Now these next ones are going to have negative answers, and I'll just explain that in just a second here. So following that same process, it's saying 8 to what power gives me 1/8. 8 to what power gives me 1/8. So we need to remember that when we have something in the denominator, we can move it to the numerator with a negative exponent. So remember, we can flip across that. That's a property rule. So 8 to the -1 is 1/8. So I could rewrite this as 1/8 is 8 to the -1 power. And then I can see that, well, x is just -1. So if you go from the number to its fraction form, your exponent is going to be negative. If you just go smaller, it's going to be a fraction. If you go larger, it's going to be larger than 1. So let's look at this next one here. Oops, this got mixed up here. This is supposed to be B, this is supposed to be C. So B, 4 to what power gives me 1/64? So log base 4 of 1/64 means 4 to what power gives me 1/64. So the first thing I'm going to do is bring that 64 up, but make it to a -1 power. Now, 64 is 4 cubed. So I'm going to have 4 to the x equals 4 to the -3. And I will see that x equals -3. And then we've got one more for C. Log base 3 of 1/√3. So that means, 3 to what power gives me 1/√3? All right, so let's think about this here. √3 is 3 to the 1/2 power. So I'm going to change that to 1/3 to the 1/2 power. And then I'm going to bring that power up to the top. So in order to do that, I need to make it negative. So 3 to the -1/2 power. And now I can see that x is equal to a negative half. Now we've got one more question here. Fill in the blank so that the resulting statement is true. If you ever take a log base b of b, you will get 1. So that means log base 2 of 2 is 1. Log base 5 of 5 is 1. Next, we're going to talk about the common log. And the common log, if you look at your calculator, it just has the log button, uses a base of 10. So if you ever see just log written, that means base of 10. So we're going to evaluate these without using a calculator, knowing that same type of process. So we want to find log of 10,000. Well, that means there's a base of 10. So 10 to what power equals 10,000? Well, 10,000 is 10 to the 4th. So 10 to the x equals 10 to the 4th. So the answer is 4. Okay, this one is log of 10 to the 8th. So 10 to what power equals 10 to the 8th? Well, the answer is 8. Determine if the following statement is true or false. The log of negative 100 equals negative 2. Now, we need to go back to some of those things we said at the beginning of this section, where the value that we're evaluating cannot be negative. So this piece must be positive. So this is false. We cannot do this. If you try to type the log of a negative number into a calculator, it's going to give you an error. We can't do it. The natural log uses e as the base. So when we were working with exponents, we practiced like, hey, e to the 7th power. So if we have those and we have e to the x equals some number, we have to be able to solve them. And the way we do that, we turn it back into a natural log. And we can natural log base, that's base e. So these are going to be done just straight in the calculator. Whatever calculator you have, you're going to find your natural log and then type in 25. Natural log 140. Natural log of e to the 7th. And what you should get are 3.2189, 4.9416, and 7. The last part of this section is going to be talking about their graphs. So can we find their domain? Can we graph a log? And then can we graph transformations of those logs? Now, because logs and exponentials, and this should be b to the x power, it just didn't copyright. Because logs and exponents are inverses or opposites of each other, the domain of one is equal to the range of the other. And then the range of the one is equal to the domain of the other. So what we can do is you can almost use the other to help you if you wanted to. Now, when we worked with exponentials, we had a domain of negative infinity to infinity, and the range was limited based on that x piece. It was either 0 to infinity or negative infinity to 0, or if there was a plus c, then it was impacted there as well. So what's going to happen here in the logs is now the range is going to be negative infinity to infinity, and our domain is the one that is limited. And that's going to be based on what's in here. So if there is other pieces inside of there, we can set up an inequality showing that that piece is greater than or equal to 0 and solve for x, and that's going to give us our domain. So it asks us to find the domain of these 4 log functions. The first one is log base 5 of x plus 6. So according to our rules, we're going to take what's inside the log piece here, x plus 6, and set it greater than 0. So we solve for x by subtracting 6. X is greater than negative 6. That means I can have any value, negative 6 up to infinity. I cannot include negative 6. It needs to be positive. It cannot be equal to 0, and it cannot be negative. That is why we do greater than 0, not greater than or equal to, just greater than. Number 2, find the domain of log 7 minus x. So take 7 minus x greater than 0. Subtract 7 from both sides. I get negative x is greater than negative 7. Now I need to divide both sides by negative 1. When I divide an inequality by a negative, it flips the sign. So I'm no longer greater, I am less than, and that becomes 7. So less than 7 means I start at negative infinity and go up to 7. Find the domain of the natural log of x minus 7. So take x minus 7, set it greater than 0. Add 7 to both sides. I see x is greater than 7. That means 7 to infinity. And the last one, find the domain of log base 2 of 2x minus 3. So take 2x plus 3, set it greater than 0. I'm going to subtract 3 from both sides. I have 2x is greater than negative 3. And then I need to divide by 2. So I get x is greater than negative 3 halves. So that means I start at negative 3 halves and I go positive to positive infinity. On this slide, we are going to talk about what the graphs kind of look like, some different things that happen. So just like exponentials can have two looking graphs depending on what the base of the exponent looked like, whether it was a number between 0 and 1 or a number larger than 1. The same thing happens with logs. So this first graph, the base is larger than 1. The second graph, the base is between 0 and 1. They will be one-to-one functions. Now, instead of having a horizontal value we cannot cross, we now have a vertical value we cannot cross. In the base form, that value is 0. In any transformation of it, that value is shifted. Some key points are always going to be 1, 0, and B1. Again, that is if there are no transformations. So we can start with these and then determine if there is a transformation, how those points shifted to be able to draw our graph. The graph looks increasing when your b is greater than 1. The graph looks decreasing when the value of b is between 0 and 1. So if we're going to graph them, the first thing you should do is draw your vertical asymptote. Note that this is different if you have x plus, c or x minus c inside here. That's going to shift your graph and your vertical asymptote. You're going to plot your first point, 1, 0. And then your key point, B1. We'll then draw a smooth curve between those points. So we're starting with our basic log graph, and the base is 3. So there's no changes to these, so we're going to start with our asymptote here. We cannot cross the vertical axis. We're going to plot our 2 points of 1, 0 and B1. So 1, 0 is here. B1 means base 1. So that point is 3, 1. 1, 2, 3, 1. And then you're just going to connect them as best as you can. And that is your log graph. So we'll do the same with the next one. We want to do log base 7 of x. So start with your asymptote. We cannot cross it. Start with your point 1, 0. And then your second point is the base, comma 1. Well, the base is 7, so 7, 1. 1, 2, 3, 4, 5, 6, 7, 1 is right there. So this one's going to be a lot steeper, just like before. The base of the exponent and made a steeper graph. The base of the log, if it's a larger value, makes a steeper graph. These two are transformations. So now we're going to do log of x minus 2, and we're going to graph that. So the base is 10. So a few things we're going to do. We're going to start with that asymptote. So take this piece, x minus 2 greater than 0. X has to be greater than 2. So 2 is the limiting point now. Everything moved to the right 2 values. So we shifted right 2. So the original graph always goes through 1, 0 and B1. So for ours, we need to transform those over. So instead of starting at 1, 0, we shift right 2. Means we're going to start at 3, 0. So instead of starting at 1, 0, shift it right 2 is at 3, 0. And then, let's see, base 10. So the original point is 10, 1, but I now need to shift it 2 to the right. It means I'm at 12, 1. So that's going to be way outside here. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's all the way over here. This is really steep for my log graph. I probably should have counted by 2s on my graph, but I didn't. All right, next one, log base 2 of x plus 5. So this plus 5 tells me I'm shifting up 5. So we're not changing anything as far as where we cross. The original graph would have the points 1, 0 and base 1. So that would be 2, 1. Okay, but now everything has to go up 5. So that's going to now be at 1, 5. And then this one's going to be at 2, 6. So 1, 1, 2, 3, 4, 5, 2, 6. And then do your best to draw your curve. I hope that these transformations are making more sense the more that we work with them. But this is the end of this section. You can go on and do the homework.